Okay. Well, thank you very much for the invitation and for staying. So I realize that I'm standing between you and the cocktail, but I don't think it will be ready before my talk is finished. So just wait and see. Yeah. I'm talking about estimation and metrology for quantum input-output systems. So my research interests are the overlap between statistics, probability, and quantum physics, and in this case, quantum open systems. Yeah. So the plan of the talk is to say a bit about quantum estimation. You've heard already from Marco, a short introduction. Then I'll be talking about input-output systems, and the main object here will be the quantum Fisher information for such systems. Then I will be looking at, okay, how do you get close to this abstract concept by doing simple measurements. And then there is a new idea of doing some sort of post-processing in order to get a bigger class of measurements. So we'll see how that works. This last topic, I'm not sure if I'll get there, but this is the connection with metastability and dynamical phase transitions for open systems. And the main message is that when you have these systems at phase transition, then you can estimate certain parameters with higher precision. Yeah, so there is a connection between these two things. Okay, I think I need to buy a new laptop. So, right, so this is the basic problem of quantum parameter estimation. So you have a quantum system with state rho, depends on some unknown parameter, and you want to estimate it. So you do a measurement, you get some data, and you do something with the data, and you get an estimator. Okay, so what is quantum about this? Well, if you fix the measurement, that basically fixes the classical model of your data, and then it's just a sort of classical estimation problem. And you can use everything you know from statistics. But actually, the main object is the quantum state, and the measurement can be chosen in principle by the experimenter. So there is an optimal measurement problem. Yeah. So what's the measurement you need to do in order to extract the maximum amount of information about rho theta? And then there is this quantum enhanced precision aspect, which is actually about how you encode theta into rho in the first place in order to be able to estimate theta with higher precision. Yeah. So I will not talk that much about that, so my state will be fixed. The dependence on theta will be fixed. Anyway, so how well can you do? So there is this quantum Kramer-Rao bound, which says that the covariance of any estimator, so theta hat is an estimator, and this is basically the variance of that estimator. If it's unbiased, is always larger than something called the inverse Fisher information. So the inverse of the Fisher information contained in the data for a given measurement M. Okay, so this is the classical Kramer-Rao bound. And now if you optimize over M, this quantity can be made smaller. And the smallest you can get to is this inverse of the quantum Fisher information. Okay? So the smallest possible error is never lower than this. And this quantum Fisher information only depends on rho theta. So you can calculate it by taking some derivative and solving some equation. Okay. I just wanted to give you this simple model. So when you have a pure state, so you start with some vector and you rotate it with some generator g, and the rotation parameter is your unknown parameter theta. Then the Fisher information is just the variance of the parameter g. Yeah, so expected value of g squared with respect to the state you started with. So bigger variance means that the vector rotates faster, so you have more information about theta. So different states with different parameters are more further away from each other. Okay, so you can have the simplest example is just you take a qubit and you rotate away from the Z state, you get this kind of model. If you compute, so here the generator is sigma Z, you compute the Fisher information is 4. So if you rotate like this, then it's clear that what you need to measure is sigma Y, or at least sigma Y is a good measurement. Yeah? So this statistical type of questions is not only about finding the quantum Fisher information, but also finding the observable that you need to measure in order to achieve that Fisher information. Okay, and then the kind of at the other extreme, you have a Gaussian shift model where you have like a coherent state with mean, which depends on theta. So you shift a state along one axis, and you want to estimate that parameter. So clearly here you need to measure this Q, and the generator of that transformation, this shifting, is P. Yeah. And the quantum Fisher information is the variance of P, so you get this F. So the more you shift, the bigger this F is. Okay, so these are two basic models, and actually you wouldn't think that there is any connection between them. But in fact, if you have, in statistics, you always want to have a large sample size. You can't just estimate the parameter by throwing one single coin, yeah? Or having a single qubit. So usually you pose the problem like this. You have n of these states, which are all rotated by the same angle, and then what can you do with that? And then you can show that this model with n qubits converges in a sort of statistical sense to this model where you shift a Gaussian state. And that's basically the Holstein-Primakov approximation. So coherent spin states are approximated by Gaussian states. In statistics, it's called local asymptotic normality. So when you have many samples, identically distributed samples, you can treat them in a certain way and they become Gaussian. So it's all related with central limit theorem and so on. And in my tutorials next week, I will tell you much more about this because it can be done. So it's a tool for optimal estimation, not only with pure states, but also for mixed states. Okay, right. So I want to talk about input-output systems. So first, open systems. So you have a system and it's in contact, interacts with the environment. So in the Markov approximation, the dissipative evolution of the system is given by the Lindblad equation. Okay, typically by ergodicity, so there is a unique stationary state, and after some time the system converges to the stationary state. Yeah. Okay, so now imagine that these parameters of the system, so H and L, the jump operators and the Hamiltonian, they are not completely known, so they might depend on some parameter theta. And you want to estimate this parameter theta. So how do you do it? Well, you could just start the system in a certain state, let it evolve for some time, and then measure it. Yeah, so direct measurements on the system. And there are many papers about this, and it's a good subject to investigate. However, this is not the setting that I'm going to talk about. So one reason is that often, especially in quantum control applications, the system is not directly accessible. The system is actually doing something, and you are monitoring it, indirectly. So you don't want to measure the system directly. Also, the system will need to be initialized repeatedly, because, as I said, after some time it goes to the stationary state, and that's not very interesting, right? And then the other reason is that information about the dynamical parameter actually leaks into the environment. So it's not a good idea. If you have access to both system and environment, you rather look at the environment than the system. Okay, so that's the setup that I'm actually, I find more interesting. So an input-output system, when we do quantum engineering, we can actually engineer systems so that it's not just an atom in some open environment, but you can control the input and the output of that system. So in this case, you describe, as usual, with the SLH formalism, the input is some bosonic noise, and the unitary evolution of the system and the noise together is given by this quantum stochastic differential equation. Okay, so it's just some mathematical tool that you use, but it's basically describing the unitary at time t corresponding to the interaction between system and environment. Okay, and you have the Hamiltonian of the system, and you have the coupling of the system times the increment of the creation operator of the input. Okay, and my system identification problem is the same. So if there is some dependence on H or on theta in the dynamical parameters, I want to find what that is. So there are several questions you can look at. So which parameters can be identified? It's not, this is like a black box. So it's not obvious that information about some parameters comes out of the box. If there is information, how much? So what's the quantum Fisher information for those parameters? The output here is also a quantum system, is the sort of light emitted by some atom in a cavity or something. So you do measurement on it, but you can think of it as a quantum system. Right, so of course, all this is related to ergodicity and spectral gap and so on. How does it go? Which measurements are informative? This is more practical if you really want to do this kind of stuff. And how do we achieve high estimation accuracy? So that would be more a setup in which maybe this system couples with some external field and you want to use it as a sensor. So how do you design your HNL for high sensitivity? Let's say. So we are in good company here. So some of the most well-known systems are input-output systems. So the atom maser of Haroche and LIGO, they are input-output systems. And here, if you want to do some feedback control, you need to know actually the parameters of your system, right? It's all based on knowing the model. And here, also you need to know your system because you need to distinguish between the signal and other things that might actually come from wrong modeling. Yeah? So system identification is like the other side of control theory. So I guess that's where I relate to this conference. Right, so we want to do system identification. Okay, so now I said that my idea is not to measure the system because it's a black box, but to measure the output. So if you want to understand how much information there is in the output, you need to understand what's the quantum state of the output, right? So that's what I want to show in this slide. And to do that, you can discretize time. So make very small time bins and see what happens in the environment in each of these time bins. And most of the time, nothing happens. There is no photon emission. And that corresponds to applying this Krauss operator on the system. So when you discretize time, this continuous evolution becomes discrete, and is described by Krauss operators at each time step. When there is an emission, so there are several of these jump operators, so each corresponds to a sort of type of photon. And when there is an emission, you apply this operator, which is more or less the jump operator, and then there is a little of this unitary evolution. Okay, so that's what happens if you are actually counting photons, but you don't have to do any measurement. So if you don't do any measurement, then all these possibilities occur in a coherent superposition. So the joint state of the system and the output is going to be the superposition of all these possible trajectories in which you have obtained certain information in each of those time bins, and every time you have applied the corresponding Krauss operator on the system. So this kind of state is called the matrix product state or continuous matrix product state in quantum information. And that's the kind of state that I'm interested in. It contains information about theta through the Krauss operators. Okay, so now how do we find the quantum Fisher information? So I told you in the beginning, when you have a rotation model, the quantum Fisher information is the variance of the generator. So I need to find the generator and then compute its variance. This is a rotation model because the system together with the output are in a pure state. Okay, now there are, yeah.
Sorry, the previous slide, the matrix product state lives on the space of the system plus some other stuff?
Yeah, so this is the system. This is the initial state of the system. And this is the output. So each of these J's is a time bin of the emitted photons. So it can say no photon or one photon of type I don't know what, and so on. Yeah? So it's a very big state, and it increases with time. Yeah. So the output is a bosonic field. So it's a Fock space.
In an experiment, do you know every value of every jump time?
Well, it depends what experiment you are doing, but it is like this, yeah, the quantum state. Okay, so this is again the state of the system and the output. It depends on this theta. So you need to find the generator. You need to basically take derivatives with theta. So in your parameter space, you are sitting somewhere, and there is this tangent space, so you can go in different directions by changing parameters. So you get the derivative of your dynamical parameters, and then you want to find how does the state change with the dynamical parameters. And if you use stochastic calculus, you can compute this, and you get this generator appearing here. And the generator turns out to be a quantum stochastic integral. Okay, so that's where this stochastic stuff is useful. But anyway, there is a generator, and it looks like this. It depends on which direction you are taking in your parameter space. So it comes here in the derivative of L, and here in this operator ED. It's linear in the tangent vectors. Okay, so this is an operator. I put a square root of t in front of it, because one of the conjectures that we still have to prove is that actually this f here satisfies the central limit theorem. So I call it a fluctuation operator. Okay, and now the theorem is the following. So I want to compute the quantum Fisher information matrix, because so there are now several parameters. In principle, I don't need to know anything about H and L. So you'll have a matrix, and it's the covariance matrix of these generators. So expected value of G with different directions. Now this is the Fisher information for the output state at time t. So I observe, or I just capture all this quantum state, and how much information there is in it. Yeah. So it depends on t. Typically, it will grow linearly in time. And the rate of that growth is this FAB, this matrix. And now the theorem says that this matrix is like an inner product on the tangent space. Yeah, so it's a positive matrix. And it has this expression. Okay, so that's perturbation theory. And you have this L-1 appearing here, the inverse of the Lindblad generator. Well, so there isn't any inverse of Lindblad generator, but you can invert it on the orthogonal of the stationary state. So this expression makes sense. Yeah. Also, you see that it's manifestly positive because it's the expected value of something that depends on A, and the same thing depending on B. Anyway, so the important thing or something to note about this is that you have the inverse of the Lindblad generator, and that is of the order of the 1 over the gap, the spectral gap of the generator. So that suggests that when the spectral gap is small, then the Fisher information will be large. Okay, so that's the basic idea why systems at dynamical phase transition or metastable systems which have small gap might have large Fisher information. Okay, now if you look in more details at this formula, you find several things. So first of all, sometimes this whole thing is 0. So there are directions in the parameter space which when you move, you change your parameters like that, there is no signal coming in the output state. Okay, so these are the non-identifiable parameters. So these directions look like this, and this is, you see that this is just the generator of a rotation. So you rotate your Hamiltonian and your jump operators by the same unitary. When you do this transformation, the stationary output doesn't change. So okay, I didn't say, but because I'm looking at the output for long times, I always converge to stationarity. Yeah? And although by rotating H and L by some unitary, something changes inside the box, the output doesn't change. Okay? So there are non-identifiable parameters, and they correspond to rotations, or you can add a constant to the Hamiltonian, which just gives you a phase. And in fact, we can show that these are all the unidentifiable parameters in this setting. And then, so this is this sort of subspace of the tangent space, okay? And then there is a sort of complement of this, which is the tangent space of the identifiable parameters, yeah? There isn't a unique choice of how to split the tangent space into this one and the other one, but there is a sort of canonical nice one, which is defined by this equation, okay? I don't have a very good intuition about this, but this splitting of the tangent space is covariant with all this group action and so on. And also, if you use that splitting, the Fisher information in this identifiable space has a very simple formula. So you go down from this to this, okay? We don't really understand why, but it's very nice. Anyway, so on this identifiable space, so when you cut off these orbits of parameters that cannot be distinguished, you get a manifold. And on this manifold, the Fisher information is called information geometry. And we want to look more at this. Something that I will do next week is not only we have the Fisher information, but like in the case of the Holstein-Primakov, where we said when you have n qubits, this becomes Gaussian somehow. The same thing happens here. When you look at this output for a long time, the output state becomes Gaussian when you look at it from the right point of view, statistical point of view. So you will get a Gaussian state on some CCR algebra. Okay, good. So up to now, I haven't done any measurements. I just said this is the quantum Fisher information. This is the best thing you can hope to get by doing whatever measurements you want on the output. Yeah. So now, can we do? How close can we get to this? Now, on the other extreme is the simplest thing you can do is count photon or do homodyne measurements. Even if you do photon counting, analyzing the whole trajectory with all the waiting times is not easy. You could apply maximum likelihood to estimate the parameters, yeah, which is fine, but in real time you can't do it. The simplest thing you can do is just take the total number of photons emitted in a time t, forget about all the waiting times, and use that as an estimator somehow. Yeah? And this theorem tells you how well you can do with that. So basically, when you take the total number of photons, that will satisfy a central limit theorem. So the total number of photons will have a Gaussian distribution, which so you'll have a Gaussian distribution, and its mean will be something like T m theta. So it grows in time linearly, and this m theta carries information about theta. But of course, there is the variance. So you need to compute the signal-to-noise ratio, and that's the Fisher information. So this is always smaller than the quantum Fisher information, of course. And these numbers can be computed explicitly. So you have formulas for them. Similarly, if you do homodyne, exactly the same thing happens. So you can compute how much information there is in the integrated homodyne current. OK. So one example we looked some time ago is the atom maser with the Jaynes-Cummings interaction. So the atoms interact with the cavity modes through this unitary. In principle, it's a discrete time model because atoms come and interact and they go. But often, the people model this by putting a Poisson distribution on the atoms, and they go to some continuous time approximation. So there's no point in going into details, but you get this master equation with 4 jump operators corresponding to absorbing excitation from the atom or from the, so actually from the bus, because the cavity is in a thermal bus and so on. Okay, what's interesting about this atom maser is that it has a very rich structure. So if you vary that interaction parameter, this Rabi angle here, and you look at the stationary state in the cavity, so this is like distribution of photon number in the cavity, you see that there are some phase transitions. Well, people call them phase transition. It's not, mathematically speaking, is not a phase transition, but there are metastate for certain parameters. You have bistability. So you have a blob of the stationary state here at low photon number and another one at high photon number. So that's interesting. And then the question is, what happens with the estimation problem? Is there some interesting thing there? So if suppose I want to estimate phi, and because this model is actually more or less classical, there are jumps up and down on these Fock levels. It's like a burst death process. You can compute many things. So first of all, the quantum Fisher information is proportional to the mean photon number in the cavity. So this picture here also is the picture of the quantum Fisher information. Okay, so it's this red line here. And then you can do all kind of counting measurements. So you count, you measure the outgoing atoms. Are they in the ground state or the excited state? You can, in principle, also measure leaking photons and so on. And you get, by analyzing these processes, you can compute the Fisher informations, and you get these other kind of curves. And I just want to point out that you see here at this point where you have a maximum of the mean photon number in the cavity, you have 0 Fisher information for certain statistics. Okay, so this if you take the total number of counts, because being at the maximum means that the derivative is 0, so there is no sensitivity to changing parameters. Yeah. So it's very important, to treat your data well. Now, unfortunately, so these two pictures might not correspond to the same parameters, but this red curve here is one of these blue and black here, corresponds to total numbers, and it has very bad behavior here. If you actually take all these inter-arrival times into account, you just do maximum likelihood estimation on the full trajectory, you get this Fisher information. So you see that this 0 is resolved, and this curve sits somewhere under the red curve. Is still much smaller than the quantum Fisher information, but it's good. Okay? So it's an interesting model to see a bit what happens with different measurements and different ways to treat the data. Okay. So, by the way, so if there are any questions, please ask me. No? Okay, so, but can we do something more? So we can do homodyne and maybe heterodyne and counting, take the total number of photons or integrated current, maybe do maximum likelihood, but I would like to have more general measurements because this quantum Fisher information typically is not going to be attained by simple measurements. For some time I had this idea, it's kind of desperate situation, so what can we do? Maybe place another system in the output of this is my system that I want to estimate. Instead of measuring directly here, I put another system and then measure with my usual homodyne and photon counting afterwards. Yeah? It's not obvious why this should be it should be a good idea, but it's kind of the only thing you can do in some sense. So this is a concatenation. So we know, well, from John, we know how to compute the parameters of the two systems together. You just, this is the Hamiltonian, and you just add the coupling operators. And because this guy is just doing some additional rotation on the output of the first one, the quantum Fisher information actually doesn't change. Yeah, it's just some additional rotation. However, the measurement that I'm doing now on my system is this stuff put together, so it's a more general class of measurements. Okay, but then the question is, okay, so what parameters do I put here, this H tilde and L tilde? And one of the things I thought is, well, there is one sort of canonical situation where the two systems together could end up having a pure stationary state. Pure. Okay? And pure is more quantum mechanical, and you hope that it's better, easier to handle. And then when I looked in the literature, I found that actually this exists already. So in this paper, they call it coherent absorber, because you have an input, you have your system, you have this absorber, and together they will be in a pure stationary state, and that means that the output is going to be vacuum. So there is nothing coming out because the system goes to this sort of ground state and it just stays there. Yeah? So this is a very nice situation because then the output is a trivial state. Yeah? The problem in the previous case is very hard to analyze all these quantum correlations in the output. Okay, so how do you find this absorber? How can these two be in a pure stationary state? They must be, you must have a Schmidt decomposition of this type of the stationary state. Yeah, so these are the eigenvectors of the two separate reduced states. Okay, and then the parameters of the absorber are given by these equations. But roughly speaking, it's minus. Nice. So now what I want to do is I have my system with unknown parameters. I want to put an absorber after it, which has the same if it has the same parameters, nothing will come out. Okay, so I want to do a sort of null measurement. But of course, I don't know the parameters, so I can only put an absorber which has approximately the same parameter. Right? So I'm going to consider theta, the unknown parameter is theta 0 plus some perturbation that I want to estimate. So what will come out here will be 0 when I have perfect matching, but something will come out and will tell me what delta theta is. Is this useful? Well, I think null measurement is conceptually simple and is actually used in experiments. This can be implemented adaptively. So as you get more and more information about theta, you change this theta 0. So you can use a feedback loop to change the parameters of this absorber and get a better precision. And also you can, it's easy to calculate signal to noise ratio, so the Fisher information, because the signal to noise is always of the form some derivative, and you will see in the next slide that that makes computations very easy. Okay, so let's do that, and let's consider the homodyne measurement. So I'm going to do homodyne after the absorber. So you do homodyne and you take, the simplest thing to do is to take the integrated homodyne current, so like the first moment. Yeah? And the Fisher information will be, like we said, the derivative of the mean squared divided by the variance. But the variance of the homodyne is 1. Well, if you normalize by t, it's just a Gaussian state. So this is just this thing squared. Okay, you can also take the second moment. So you take quadratic functionals of this type. Because it may be that in some situations, the mean homodyne current is 0. Right? But the quadratic thing is still contains information. The signal to noise ratio in this case will be this. So it's like the inner product between this kernel that you use and the derivative of the correlation function of your output divided by k squared. So this is the signal to noise ratio for an arbitrary k. Now I can optimize over k's, and the optimal one will be k equal to c dot, so the derivative of the correlation function. Yeah? So the Fisher information will be the norm square of the correlation function. So at least for these two estimators, you can calculate the Fisher information. Okay, so now I haven't really solved this problem completely, but I looked at many models, simple models, and there seems to be hope that you get something nice. Okay, so the simplest model you can have is like several levels, and so I want to describe this reference absorber system. So you have several levels and the jump operator that goes down to the vacuum here. Sorry, no, that's not what I'm doing. So forget about this separation system and absorber. Just take them together, and they have the property that when theta is equal to theta 0, there is a pure stationary state. Okay, so that's my joint system here. So I have this L, and the stationary state is 0. I have no Hamiltonian. Okay, it's a model. I can go beyond this in some special cases, and it seems still to work. And then on top of this, you add the perturbation. So that's because theta is different from theta 0. Okay? So here I'm going to add a perturbation, a Hamiltonian perturbation. And this is basically making connection between the vacuum and the different other states in my basis. Yeah? When you do that, the stationary state changes. Is not anymore this vacuum, so you'll have some mixed state. And you can use perturbation theory for the stationary state as function of the unknown parameter. So the unknown parameters are this u. And this means that I have one parameter for sigma x between these levels and the other for sigma y. OK, and then you start computing. So first of all, I didn't put any parameters for jumps between these levels, because you can show that the quantum Fisher information for that is 0. And you can imagine why, because this is a sort of rotation inside here, but you need to get from the vacuum there in the first place to see that rotation. Yeah? OK, that's not too bad, because actually you have enough parameters here to estimate all your initial parameters in your system, which are of the order d square, because the Hilbert space dimension of the two systems together is d square. Yeah, so there are actually d square of these levels in the joint system, and there are d square of this sort of jumping parameters between 0 and other levels. Yeah, I don't need to see all these other parameters. OK, so that's 0. And then you go to the first level, and you find that for that perturbation, the quantum Fisher information is this. So by the way, it goes with 1 over epsilon square. So again, if you are sort of metastable, so very low probability of jumping to the ground state, then the Fisher information is large. You see this thing again. And then you find that it's achieved, this Fisher information is achieved by the first moment homodyne statistic that I described before. So you just do homodyne measurement, take the total integrated current, and that achieves the quantum Fisher information. What this says is that in this case, the output state is actually like a coherent state. It's just a coherent state with constant mean in time, and you just do the homodyne of that state. So that's for this parameter. Now, what about going between these two? You need to go to the first and second level, and actually everything will be in there. But actually, it's not true. You have all the higher order moments have information about some parameter. So it's simply, in this model, it's simply the higher you are, the higher moments you need to look at in the homodyne current. But they will achieve the Fisher information, the quantum Fisher information for that parameter. OK. So really what we want is to have a general theory now where you don't just have some L0, but you also have some H0, which leaves the vacuum invariant. And I've done a few calculations with models of this type, including an H0 here. And it seems to work, but I don't have, it's still a conjecture. So the conjecture would be that with simple measurements like homodyne, you can actually get this quantum Fisher information when you have this quantum absorber. OK, so what time is it? It's more or less time, yeah? So I will skip this bit, so maybe I'll talk about it next week in the tutorial if you are here. Like I said before, maybe just show this slide. So in the atomizer, we said that there are these phase transitions. These phase transitions are visible if you do the filter of the cavity state. When you are somewhere here, so away from the phase transition, you just see some jumps up and down between the energy levels. If you are here, you see long periods of being somewhere here. In the photon counting distribution, or the counting distribution of the ground state and excited state atoms that come out, in this case, you will see a nice Gaussian distribution, so central limit behavior. Here, you will see when you are in this sort of period and when you are in this period. Yeah? So this is a bimodal distribution of the photon counting. And the variance of this, so here the variance is of the order t. Here the variance is of the order t square. And we said that variance sometimes is the quantum Fisher information. So here the variance grows linearly, here grows quadratically in time. over the gap. So for a very long time, you have quantum Fisher information that increases like t squared. And that's what we call Heisenberg limit for a dynamical phase transition. The number operator would have to be the generator. So what parameters have number operator as generator? These are phase rotations. So if you just put a phase plate in the output, and you want to measure its, the phase that it applies to the photons, you better have outputs of this type, which have superpositions of low and high photon numbers. So it's like a GAZ state. So, okay. So the outlook, so we are viable in nonlinear systems, at least when you look at this stationary scenario. You get a nice manifold, which is the quotient with this group of transformations, of sort of gauge transformations. And there is the quantum Fisher information is a sort of Riemannian metric on this. So it's the real part of the covariance of the generators. I didn't say what's the imaginary part. The imaginary part has to do with some commutation relations of this CCR algebra that I said exists in the limit. So there is a quantum Gaussian state in the limit. And I will do that in the tutorial. Now, Fisher information depends on measurements and on statistics that you apply to or what methods you use in treating the data. And then there was this idea with the post-processing using coherent absorber. It seems that it simplifies a lot the estimation problem, and it seems that you can reach the quantum Fisher information in many situations. So dynamical phase transitions. So we have done a lot about this stuff also for linear systems. So there is a sort of parallel theory. In the linear system situation, you look in the frequency domain and you use transfer functions and power spectrum and so on. But we have this kind of theory. And what I'm interested in is deriving the central limit of this Markov dynamical systems. Using coherent feedback, I didn't really do any feedback because I don't have any results on feedback, but in principle, you can put your black box in a bigger circuit and maybe get better information about the parameters. If you just put a post-processing after it, the Fisher information is the same. But if there is feedback, that completely changes the parameters of the system. And okay, I kind of swept under the carpet that everything is nice, pure, and quantum. But in reality, you have channels that are not accessible. So I'm assuming that I measure all the output. So more realistic, you want to treat the situation where you have two channels. One is the one that you can measure. The other one is more noisy. You still get, also the input state was trivial, except in the linear systems, it's easy to analyze the situation with time-dependent inputs because you go in the frequency domain, but for nonlinear systems, it's not obvious. And then the time-dependent parameters. So in LIGO, they measure a time-dependent parameter. I don't know exactly how my theory can be adapted to time-dependent, at least with slow. Thank you very much.